Yes, there we go. Now we're recording. This symbol up here means that we're recording. Good. So I thought I would go over the exam practice questions that I've posted on Canvas. Already the answers are up there, but I think there's some value to my going over it too. So the first question is about the mass spectrum of 4-heptanone, which I gave the structure. I clarified the structure a little bit here on ChemDraw. And so the question is asking to give 3 fragments other than the molecular ion and other than this example. You can't write down the same example and get credit, obviously. So in order to answer this, what you need to know is that when organic compounds are put through a mass spectrum, they break up into fragments, and we discussed some of the ways that they can fragment. One of the things we said is really every single covalent bond can break. There also is the chance, since we have a ketone, for alpha cleavage. So we should expect to see alpha cleavage products. Of course, this compound is symmetrical, so it doesn't matter on which side the alpha cleavage occurs. But we would expect to get propyl cation, and we would expect to get the other piece. So even before looking at the mass spectrum, that's a couple of fragments that we can expect to get. So you could write that fragment like this, or you could write the fragment with the plus charge on oxygen, either way.
Yay! Okay, wait.
Like that. Either way is fine. They're just different resonance forms of the same species. And so we need to figure out the weight of this species. It's going to be C4H357O. So let's see. And I, of course, don't have a calculator. I have one in my cell phone. There's, of course, one that's an app. C3, so 3 times 12, plus 7 for the 7 hydrogens, plus 16 for the oxygen. That gives 59. So whichever way you draw this, you would also need to write m over z equals 59. You see how we did that over here with the ethyl cation? So that one we would expect to see. There could also be fragments of the butyl group, but maybe for that, we'll look at the actual spectrum before I get too far ahead of myself. That's the one with proton NMR. So this is the one. There we go. There's the mass spectrum. So first of all, let's see if there's a peak at 59. It's very small, but there is. Or is that supposed to be 58? Wait a minute. 3 and 2 is 5 and 2 is 7. There's no hydrogen here. Yeah. Oh, I know what I did wrong. I did C3H7O. It's C4H7O. Let's try that again. Wait a minute. 3, 5, 7. Seems low, but, well, I guess not if there's a triple bond between the oxygen. So let's try that again. 4 times 12 plus 7 for the 7 hydrogens plus 16 for the oxygen. That's more better, 71. Let's see if there's a peak at 71. I bet there is a significant one. Yep, sure there is. It's very large. So what you would write is your choice of either of those structures, and then m over z equals 71, just exactly like we did in the example. So if you have a question like this, you need to follow the format. You should show a structure, and that structure had better be a cation. Remember that in order to be detected on a mass spectrum, a species must be charged. And really, for our purposes, that species will always have a charge of exactly +1. So the ethyl cation, we exclude that since that's already given in the example. So we've got one fragment. Let's see if we can find some more. Well, I see a peak at 15. There, by the way, is the peak at 29 for the ethyl cation. 15 is one we talked about in class. That's going to be CH3 plus. So you would write CH3 plus M over Z equals 15. That's another fragment. So let's see. Here's one, there's one. We need just one more. Are there any propyl cations present? Propyl is C3H7 plus, and there are propyl groups on either side of the carbonyl. We could certainly get that piece. So propyl is C3H7 plus. 3 times 12 is 36, plus 7 more makes 43. And there is indeed a significant peak at 43. And you could really do either. You could write either CH3, CH2, CH2 plus, or take your pick. You could reason, well, that's a primary carbocation. It's going to rearrange. Probably we're going to get the isopropyl cation from that after a hydride shift. So either way, write exactly one of those. That's going to be at M over Z equals 43. And we've already got 3 fragments besides the ethyl cation and the molecular ion. There's also a peak at 99. 99 is 71 plus 28. 28 sure sounds like 2 CH2s because each CH2 is 14. So it looks to me like we have a fragment, at least that's an isomer of that. That's going to be C1, 2, 3, 4, 5, 6, 6, C6, H3, 5, 7, 9, 11, O. And that's going to be at M over Z equals 99. So just amongst those, we've got 4 of them, and we only needed 3. And I'm sure there's others as well, but those are amongst the most obvious ones. So what you need to know in order to solve a problem like this is you need to look for pieces of the molecule that are then cations and see if you can find those masses in the mass spectrum. You certainly don't need to, I also just realized chat's off. You certainly don't need to identify every single peak. I sure couldn't. But that's how you go about it. You look for pieces of the molecule, you write the structure of the piece, not the formula, the structure, and then you write how much that piece weighs. And you just do that however many times the question asks you to. There should be plenty of fragments available. These are just some of them. These are the ones that came readily to my mind. And that's about it for that one. Questions on that one? Wow, we got 9 people. That's actually a lot. You have to remember that when it says participants up here, that includes me. So there's 9 people other than me. Good, so much for the mass spec problem. Let's take a look at these IR spectra. So where can I put chat? We'll put it over here for now. So these are our 6 choices for IR spectra. Maybe I'll put that one over here. And I can't make that window any smaller. All right. So spectrum S, what do we see? Well, what jumps out at me, first of all, is the big carbonyl stretch at around 1720. That narrows it down to B, C, or D. Nothing else is a carbonyl. I also can tell that there are CH stretches both above and below 3000 wave numbers. There's your 3000. So that means that we've got both alkyl CH bonds, sp3 hybridized CH bonds, and sp2 hybridized CH bonds. So we need either an aromatic ring or an alkene. That rules out C because C is saturated except for the carbonyl. Not to mention that it's a carboxylic acid. And if we had a carboxylic acid, there'd be this huge peak obliterating pretty much all of the upper frequency end. So we know it's not that. It also can't be D because D is also saturated except for the carbonyl. So it has to be B. And let's see, I can't write a B on this, but spectrum S has to be B because we've ruled out everything else. Spectrum T, well, it jumps right out at you. Immediately you see this nice, smooth, parabolic peak at round and about 3,400 wave numbers. By the way, all of the CH bonds are on sp3 carbons. I don't see a carbonyl. So basically, I'm looking for an alcohol. There's only one alcohol, A. If there were more than one alcohol, then you would look for the one that's fully saturated in order to match this. That's about all we can tell from this spectrum, is that it's a fully saturated alcohol. We sure couldn't tell which one. But there's only one compound that satisfies that description, which is A. So spectrum T is A. Moving on to spectrum U, there's very little to see here. There's no alcohol or carboxylic acid. There's no carbonyl. This is at about 1450. It's much too low to be a carbonyl. All of the CH bonds are sp3 hybridized. So there doesn't appear to be any alkene. There doesn't appear to be any aromatic portion of this molecule. There's no alcohol. There's no carboxylic acid. There's no carbonyl. So it can't be this. It can't be this. It can't be this. And it can't be this. That leaves it down to E and F. And of the two, if it were F, we'd see CH stretches above 3,000 wave numbers, just above 3,000 wave numbers. We don't see those. So it has to be E. So that's how you do this. You do it partly by narrowing down, and certainly also by looking at what functional groups are not present. That's equally important with IR as to the functional groups that are present. And finally, spectrum V looks to me like, once again, we don't have a carbonyl. That peak is way too weak to be a carbonyl stretch. Looks like we have CH stretches both above and below 3,000 wave numbers, but there's no OH, there's no carbonyl, so it can't be D, it can't be A, it can't be B, and it can't be C. So we've already had E. The only one left is F. And that makes sense. We've got an alkene in F. So that's going to give rise to sp2 CH bonds. And we can see their stretches at just above 3,000 wave numbers. So that's how you go about a problem like this. You do it partly by process of elimination. Good. Any questions on any of those spectra? I think what I will do, if no one objects, is do the carbon-13 NMR spectra and then do the proton NMR spectra and the combination spectroscopy problem. That way I can put away those two documents and just leave this exam open. No, we don't want you yet. Good, here's our carbon NMR spectra. And here we have our actual carbon NMR spectra. So these are the compounds that it could be. The first one looks like it has 4 peaks in the aliphatic range, the normal alkane range, and one that can only be a carbonyl carbon. Nothing else shows up that far downfield. So this also, in fact, rules out the two carboxylic acids, because carboxylic acid carbonyls are at more like 165, 170. But let's say you didn't know that. We can also rule out G and J because there are no aromatic carbons. That whole region of the spectrum is clear. So it can't be G or J. The only ones left with carbonyls are H and I. So of the two, we're looking for one that matches this spectrum. This spectrum says that there are 5 different carbons all told. There's 5 peaks. And that matches compound H. All 5 of those carbons are different. You can verify that using the chlorine method that we discussed in class. Compound I has only 3 types of carbons. These 2 methyl groups are the same, and these 2 CH2s are the same. So there's only 3 types of carbon in I. So it has to be H. So spectrum W is H. Looking at spectrum X, it says for spectrum X, there are exactly 5 peaks between 120 and 135 parts per million. If something's hard to see, I would certainly give a hint like that. I think all the questions in my exam are fair. I think it's easy enough to see everything. And if I had any doubt, then I gave little hints like that. So there's 5 peaks here and a 6th one over here. All 6 of those peaks are in the aromatic region. That's where aromatic carbons show up. So it must be either G or J. Those are the only 2 that are aromatic. Well, we also have a peak at about 173 parts per million. Both G and J have a carboxylic acid carbonyl, so that's going to be where that shows up. That doesn't rule it out, narrow it down. Both G and J have an aromatic methyl group, and I would say 23 parts per million is quite reasonable for that. So again, that doesn't help us to narrow it down. What helps us to narrow it down is that there are 6 aromatic carbons. All 6 aromatic carbons are different. That's certainly true for G. All 6 of these carbons are different. And you can verify that by replacing each carbon in turn with a silicon atom. And you'll notice that you get 6 different compounds. If you tried that with J, you would not get 6 different compounds. You'd get 4 different compounds. This carbon attached to the carboxylic acid is one type of aromatic carbon. There's the 2 carbons that are ortho to that carbon. There's the 2 carbons that are meta to that carbon. And there's the carbon that's attached to the methyl group. So we would see only 4 peaks in the aromatic region, not 6. That means that spectrum X must be G, not J. So G is the correct answer there. What about spectrum Y? Well, there's only 3 types of carbon. This one that's the most downfield sure looks like it's attached to oxygen or something quite electronegative. It's not quite far down enough to be an alkene carbon. You wouldn't expect to find an alkene carbon all by itself, generally, unless you've got a symmetrical compound. So do we have any alcohols or ethers or anything? We have an ether right here. We also have this cyclic ether. So it looks like it's one of those 2. K has 1, 2, 3, 4 types of carbon. The methyl groups are all the same. The central quaternary carbon is another type. The CH2 is another type, and the methyl group is another type. This methyl group is different from the methyl groups on the tert-butyl group. Whereas on L, how many types of carbon do we have? We have these 2 that are attached to the oxygen. That's one type. We have these 2 that are one further away from the oxygen. That's another type. And then we have the unique carbon on the other side of the ring. That's a third type. So we would expect to see these 2 carbons maybe round about 60 or 70 parts per million, and the other 2 types of carbon further upfield. And that's exactly what we see. It's interesting to note that the most upfield peak is also the shortest. You can't bet your whole life on that, but that to me is not surprising because that corresponds to the carbon that's unique. There's only one of it. The other 2 are doubled, and that will tend to make the peak taller, other things being equal. It's not an exact thing, but it tends to make the peak taller. So I think spectrum Y is L. Call it tetrahydropyran if you want to. I won't insist. And then spectrum Z also has 3 peaks, one of which is extremely far downfield. The only thing that shows up in that area is ketone carbonyl carbons. So we're looking for, first of all, let's look for carbonyl compounds. We've already dealt with G and J. It can't be either of those because there's no aromatic carbons. So it must be H or I. We've actually already had H, so it must be I. Let's say we didn't know that. We look on spectrum Z and we see there's only 3 peaks. So there's only 3 types of carbon. And compound I is consistent with that. There's only 3 types of carbon. One here, the 2 methyl groups, one here, the 2 CH2s, and the unique carbonyl carbon. So spectrum Z has to be compound I. And that's about it. You can get a lot of information from NMR spectra. I think that's all we will need of this document. Let's move to the back. I should mention, on these practice problems, I wrote in the practice problems which exams you'd find them on, whether exam 1B material or exam 1A material. And of course, on exam 1A, remember, there's not going to be any NMR on exam 1A. Exam 1A is chapters 12, 15, and 16. And exam 1B is where all the NMR will be. Exam 1B will be on chapters 12 and 13. So IR and mass spec is also fair game for exam 1B. So this is very much the same type of question as we just had. We've got proton NMR spectra first. And here I actually gave them 6 out of 8 choices they had to pick. So let's look at that first spectrum. First of all, we can see there's 4 different types of hydrogen in a ratio of 4:1 to 4:6. Again, remember from the integrals, all you get is the ratio of the carbons. I'm sorry, of the hydrogens. Looks to me like we have 2 equivalent methyl groups, 2 equivalent CH2s over here, and 2 equivalent CH2s over here. What could the broad 1H resonance be? Well, the most likely thing is either OH or NH. Those usually are quite broad and they can show up anywhere. And they generally also don't contribute to the splitting. So we're looking for something with 3 different types of hydrogen in a ratio of 4:4:6 with either an OH or an NH. And compound X fits that description. So I think X is the best answer for spectrum A. Spectrum B is a little more complicated. We have, first of all, hydrogens in a 3:2 ratio, and the 3H resonance is a triplet, and the 2H resonance is a quartet. We went over that in class. That's an almost sure sign of an ethyl group. In fact, it might just be a sure sign. I can't think what else it could be. The only thing that varies is what the CH2 is going to be attached to. And with the CH2 being at about 2.5, that makes me think it's not next to oxygen, but maybe next to something like a carbonyl, or they could be allylic hydrogens. They could be next to a vinyl group or also an aromatic ring. They could be benzylic hydrogens. Meanwhile, further evidence that we have an aromatic ring and therefore the possibility of benzylic hydrogens is down here. Remember, aromatic hydrogens show up between 7 and 8 parts per million, typically. If there's something very electron withdrawing, they could show up downfield of 8 parts per million, but most always they're between 7 and 8 parts per million. And they're in a 3:2 ratio for a total of 5 aromatic hydrogens. We said in class, aromatic hydrogens often all fall on top of one another, even if you'll often even just see a 5 hydrogen resonance in the aromatic region. And that indicates you've got a monosubstituted benzene ring. Well, in any case, we've got 2 compounds with benzene rings. We have ethoxybenzene and we have ethylbenzene. In ethylbenzene, the CH2 is benzylic. And so we would expect those hydrogens to show up at maybe about 2.5 parts per million. The CH2 in the ethyl group on ethoxybenzene is next to an oxygen. We would expect those hydrogens to be at more like 3.5 or 4 parts per million. It's a very big difference. It's easily an entire part per million. So that's how you tell the difference between S and T. And of the two, T matches better. So I think spectrum B is T. It's ethylbenzene. Moving on to spectrum C, we have another real common thing that we've run across multiple times before. We've got a 6-proton doublet and a 1-proton multiplet. That means that we've got 2 equivalent methyl groups that have 1H next door to them. And we also can see that 1H over here. That 1H will then have all 6 hydrogens of the 2 methyl groups right next door. So you would expect 6 + 1 = 7 peaks. With that many, we generally just give up and say multiplet. Though I could have said septet, or 7 lines, or something like that. But these 2 resonances are the sure sign of an isopropyl group. We also have a 3H singlet, meaning that there's a methyl group that has no adjacent hydrogens. As it is, we didn't even need to look at that. Oh, I lied. There's 2 of them that have isopropyl groups, aren't there? So we need to find which of those has a 3H singlet, has a methyl group that's not next to any hydrogens. And U has no methyl groups. It has this CH2, which would not be a singlet. It would be split probably into a doublet of doublets, and into a doublet by this 1H, and then each doublet line split into a doublet by the aldehyde hydrogen. So Z matches much better. Spectrum C should be of compound Z. Now, what do we have in spectrum D? Well, what jumps out at me is this 1H resonance at almost 10 parts per million. Nothing else shows up there except aldehyde hydrogens. But let's say you didn't know that. You're looking then for a compound that is 4 types of hydrogen. Once again, we have a 6H doublet and a 1H multiplet. That indicates that we have an isopropyl group. The 2 equivalent methyls in the isopropyl group show up together and are split into a doublet by the adjacent hydrogen. We also have a 2H multiplet. Sounds like a CH2 with multiple types of hydrogen next door. And then we're looking for a 1H resonance that's a triplet, so it is 2 adjacent hydrogens. I don't see any other compounds with 1H resonances. The only other one is V, and the CH hydrogen there has no adjacent protons, not 2 adjacent protons. The only compound with a 1H resonance that has 2 adjacent protons is compound U. So spectrum D has to be compound U. And especially when you consider the aldehyde proton really shows up very clearly on that spectrum. So that's D. We have 2 more to go. Spectrum E looks like this. Looks like, once again, we have 5 aromatic hydrogens. So it looks like, again, a monosubstituted benzene ring. The benzene ring has 5 H's on it. And so that means the 6th place is taken up by something else. What is that something else? Well, it has to have an ethyl group. We have a 3H triplet. That's the CH3 on the ethyl group. That's split into a triplet by the adjacent CH2. 2 + 1 = 3. We also have a 2H quartet. That's split into a that's the CH2 split into a quartet by the adjacent CH3. 3 + 1 = 4. But look how far downfield that CH2 is. That can only be alpha to oxygen. There's almost nothing else that shows up there. So this one has to be the ethoxybenzene, compound S. And we talked before about the difference between compound S and compound T. The difference is very obvious. It's mostly in the CH2. The CH2 in compound S is all the way down at 4.2 parts per million. Look where it is in compound T. It's only about 2.6 parts per million. It's not a subtle difference. It's very far apart. So it's quite easy to tell when hydrogens are alpha to oxygen, as they are in this case. So spectrum E is compound S. And finally, we have spectrum F. looks to me like we have two hydrogens. They could almost be aromatic, but how are you going to have an aromatic ring with only two hydrogens? I think it's likelier that they're vinylic. And so we have two types of vinylic hydrogen and also a 2H doublet that's in the alkyl region. So these exist in the ratio 1 to 1 to 2. Are there anything with vinylic hydrogens? Well, yes, there are. Compounds W and Y have vinylic hydrogens. But we need to pick the one of these that's correct in the ratios of the hydrogens. We need a ratio of 1 to 1 to 2 of the two types of vinylic hydrogen to the alkane hydrogens. Compound Y has a ratio of 2 of these, 2 of those vinylic hydrogens, 2 of those vinylic hydrogens, and 2 of those alkane hydrogens. So the ratio is 2 to 2 to 2, or 1 to 1 to 1. We don't see 1 to 1 to 1. We see 1 to 1 to 2. So that matches W. Compound W has these two vinylic hydrogens, which are of one type, these two vinylic hydrogens, which are of another type, and these 4 alkane hydrogens. All 4 of those hydrogens are the same. You can verify that using the chlorine trick. So the ratio is 2 to 2 to 4, or in other words, all we get from the spectrum is 1 to 1 to 2. So spectrum F has to be compound W. No relation to the compound W that you can buy in the drugstore. That's completely different. And after this, we have our combination spectroscopy problem, in which we're given a proton NMR, a carbon NMR, an IR spectrum, and a mass spectrum, and asked to come up with the structure. So let's move this over here so we can work on ChemDraw. The way to solve this type of problem is twofold. First of all, you've got to work with the mass and also with your NMR spectra and be ready to subtract things. That's what I've been telling people who have come into my office with active questions. You need to be ready to subtract things. And you also need to be ready to write down pieces of the molecule. So don't try to get the whole molecule at once. Goodness, that's not possible. You want to write down pieces. And let's see, the proton NMR spectrum shows that we have a 3H resonance, a 2H resonance, a 1H resonance, 4H, and 4H. So I don't really know of a good way of getting 4 equivalent hydrogens unless you have 2 equivalent CH2s and a plane of symmetry. That's about the only way you can do it. All of these are in the alkane range, so we really can't tell too much from that. These are downfield enough that it looks like they might be next to a carbonyl. We would say they could be next to a benzene ring, but there's no aromatic hydrogens. We would say they could be next to a vinylic carbon, but there's no vinylic hydrogens either. So it's hard to see how else we could get peaks that are in this range unless there is a carbonyl somewhere in the molecule. In the carbon NMR spectrum, that's verified. We see a carbonyl peak, and that pretty much has to be a ketone. So let's write that down. We know that there's going to be a C double bond O with carbons next door. That's a piece that we have. It's better than nothing. It's a start. Looking at the IR spectrum, again, it's verified we've got a carbonyl. That's clear. We already were pretty sure it was a ketone. Besides that, I really don't see anything else. I see aliphatic CH stretches, meaning alkane CH stretches, at just below 3,000 wave numbers. I don't see any signs of an aromatic ring or of vinylic protons. I don't see any OH groups. looks to me like besides the carbonyl, everything else is just saturated hydrocarbon. And besides that, we have our mass spectrum, which gives us the molecular weight. So there's our molecular ion at 126. We had a ruler. We could maybe use the peak at 127 to give us an idea of how many carbons are in the molecule. We didn't really talk about this in class, but the M+1 peak generally arises from carbon 13s. The idea is, if, for example, well, carbon 13 is 1% of all the carbon atoms in the universe. So if you had a compound, for example, with 12 carbons in it, the M+1 peak should be about 12% as tall as the molecular ion. But again, without the actual intensity data, we can't really go too far with that. We certainly do have the molecular ion, though. So that's something. So we need to make sure that we get a formula with a molecular weight of 126. So the formulas you should try first are of two types. You want to try either CXHYO or CXHYO2. Those are the ones to try first. We can get an idea of how many carbons there are from the carbon NMR spectrum. Of course, we have to be careful. We've already determined from the proton NMR spectrum that there seems to be a plane of symmetry. How else would we get these two 4H peaks? In fact, we probably want to write down that we have two different types of CH2s. Doubled. There's one type of 2CH2s in this resonance and one type of 2CH2s in this resonance. We also can tell that there's yet another CH2 over here and a CH3 over here. And again, it doesn't matter what order you do these things in. But I would say every time you get a piece, write it down. And last but not least, we seem to have a tertiary hydrogen. Because there's this little 1H resonance over here. So if we account for all of the hydrogens, there's 4, 8, 9, 11, 14. So there's 14 hydrogens. We know for sure there's an oxygen because there's a ketone carbonyl. So what I would do first is subtract. Remember we talked about subtracting. Subtract the oxygen and the hydrogens from the total, which is 126. So 126 minus 16 is 110. Let's also subtract the 14 hydrogens. And 110 minus 14 is 100 minus 4, which is 96. And all the rest should be carbons. Well, I think 96 is evenly divisible by 12. We can find that out for sure. 96 divided by 12 is 8. I should have known that, but it's late. So we've got ourselves a formula. There's 8 carbons, 1 oxygen, and 14 hydrogens. So our formula is C8H14O. That gives us a lot of information. This formula tells us that there's 2 degrees of unsaturation. If the compound were fully saturated, it would be C8H18O. Remember, CnH2n plus 2. The oxygen doesn't affect the number of degrees of unsaturation. So there's 4 hydrogens missing. We already know where 2 of those hydrogens went. We have a double bond between carbon and oxygen. So that leaves 2 more hydrogens that need to disappear. They need to go into either a double bond or a ring. Well, we don't see any evidence of double bonds. There's no vinylic hydrogens, and there's no vinylic carbons either. So it seems that they must go into a ring. There's got to be a ring of some size. So let's see what we've got. We've got our ketone. We've got 2 types of CH2 that we could imagine go next. So let's account for those. These are those 2 CH2s. The only reasonable way to make a ring is to put the other 2 equivalent CH2s next. So this is the other set of 2 equivalent CH2s. Now all we have left is the CH, a CH2, and a CH3. Bearing in mind that carbon has 4 bonds, we can't put the CH2 here because that leaves the CH3 and the CH all alone. We certainly can't put the CH3 here. We can put this, We can, however, put this carbon over here. 2 of those bonds from that carbon will go to CH2s. In other words, we would have a carbon with 1 bond to something else and 1 bond to a hydrogen. I shouldn't have erased that tertiary carbon. I'll put it back in. That carbon is that carbon. So we have our carbonyl, we have 2 CH2s, we have 2 different CH2s, and we have a tertiary carbon to make a 6-membered ring. Completely reasonable. We know that 6-membered rings are quite common and stable. We also need to get the CH2 and the CH3 in, but there's only one place to put them. The CH2 has to go next. This is a different CH2 from the ones that are in the ring. And the CH3 has to go last of all. So here's our CH2 over here. Here's our CH3 over here. We've accounted for all of the hydrogens, and we've accounted for all of the carbons. Another way to draw this molecule would look something like this. If you did it doing exclusively line angle drawings, it would look like that. So let's count how many types of carbon. 1, 2, 3. These 2 CH2s make 4. These 2 CH2s make 5. and the carbonyl carbon makes 6. There are 6 lines in the carbon NMR spectrum. That matches perfectly. What about the proton NMR? Or what about the protons? Well, we have a CH3, that's one type. We have this type of CH2, that's another type. We have the CH hydrogen. The CH hydrogen would be here. The ethyl group, CH2, would be over here. That's the 2H multiplet. And the 3H triplet, I didn't even get to that. The 3H resonance is split into a triplet because there's a CH2 next door. So there you go. The CH2 is split into a multiplet because it is 3 hydrogens over here and 1 hydrogen adjacent on the other side. So in principle, you could have a doublet of quartets. You could have up to 8 lines. Instead, it's just kind of a heap. It's not really, or it's over here. It's not really distinguishable, the splitting, which is pretty common in cyclic compounds. Meanwhile, we have 2 types of CH2s that are doubled. There are going to be 2 4H resonances. Those are here and here. And last but not least, we've got the unique hydrogen over here. That's the 1H resonance over here. So all of the hydrogens are accounted for. So this is the answer. That was kind of a tough question, I will admit, but still doable. It's doable by being ready to subtract and by writing down pieces. Every time you get a piece, write it down so that you don't forget. Don't try to go straight to the whole structure. It's not possible in general. You need to look at what the pieces are and figure out how they go together, especially so as to be consistent with the NMR spectrum. One general rule I'll also give you: if the NMR spectra and let us say the IR spectrum seem to contradict, go with what the NMR spectra say. Within reason. If the IR spectrum says there's an alcohol, there's an alcohol. But if you're wondering which spectra kind of to hold in the highest esteem, I would say the NMR spectra. Those are the most powerful. You get the most information from those. We pretty much solved the structure just using the NMR spectrum. Good. So that's pretty much it for the combination spectroscopy problem. And with that, we're done with spectroscopy. Again, the NMR stuff won't be until, oh, I closed the wrong one. No, I didn't. The NMR spectra won't be until Friday, until exam 1B. Good. So over here, we've got a question about UV-Vis spectroscopy. That's about the only type of question we can ask about UV-Vis, because there really is nothing else. And basically what we said about UV-Vis was that the more conjugation there is in a molecule, the lower energy or longer wavelength will be the wavelength of maximum absorption. So the more conjugation, the lower the energy or longer the wavelength. Remember, energy and wavelength are inversely proportional. So we have 4 different compounds. The one with the least conjugation is going to have the shortest wavelength, the lowest value of lambda max. And the one with the most conjugation should have the highest value of lambda max. So I would just put it in the order of the least to most conjugated double bonds, or fewest to most conjugated. B has only 1 double bond, so it's got to go first. C has 2 conjugated double bonds, so it goes next. D has 3 conjugated double bonds, so it goes next. And then A with 4 conjugated double bonds will have the highest value of lambda max. I don't know that it's going to be quite high enough for this to absorb visible light. I actually don't know if that compound's known. Someone must have made it by now. But that's how you do it. The one with the fewest conjugated double bonds has the lowest wavelength or the highest energy Remember again that energy and wavelength are inversely proportional. The one that is the most conjugated double bonds will have the largest lambda max value or the lowest energy. And the reason behind that I don't think is too well understood. But the more conjugated double bonds, the lower the energy of that pi to pi star transition. Good, and that's pretty much all we can do with UV-Vis. There is not a whole lot of information we get out of ultraviolet and visible spectroscopy. Good, on the next page, looks like we're going to be drawing some resonance structures. So if this compound, we assume it's talking about this compound, or not, well, this compound before it started to undergo electrophilic aromatic bromination. Anethol is ethoxybenzene. You don't really need to know that. And actually, you don't need to have any idea what anethol is to understand the question. If something undergoes electrophilic aromatic bromination, a possible intermediate is shown below. Draw the other three resonance forms, then circle the best resonance form, the one which explains why this intermediate is likely to form. Well, we covered this quite extensively in class. You can get one resonance form by moving that double bond over. That gets rid of the plus charge on that carbon and leaves a plus charge on that carbon. You can also get another resonance form by involving the oxygen taking the lone pair off of oxygen and putting the plus charge onto the oxygen. That's a valid resonance form. And then you can get that last resonance form by shifting the pi bond over. This pi bond. So now it's between those two carbons, and that puts the plus charge on that carbon. Notice in no cases is the plus charge going to go onto the sp3 hybridized carbon. That's not possible. That one already is 4 bonds. It's not going to have a plus charge on it. So those are the 4 contributing resonance structures to the overall molecular orbital picture of the molecule. And then it says to pick the best resonance form, the one that is most likely, or not most likely, the one that best represents the overall structure, the one that contributes the most to the overall structure, and that's going to be this one, because that takes the plus charge off the ring entirely and puts it onto the oxygen atom. The oxygen is able to stabilize that intermediate by donating an electron pair. So some of the plus charge is borne by the oxygen atom. The rest is on the carbon atoms, on those 3 particular carbon atoms. So that, I think, is the best resonance form. That's like the example we talked about in class. We talked about that 4th resonance form. In the case of substituents on the benzene ring that have lone pairs on them, you have that 4th resonance form, which helps to explain why you get ortho and para substitution. No wonder the ethoxy group and the carbon that took the bromine are para to each other. That's going to be that's going to lead to the major product, the para-brominated product. So you could, in principle, draw that intermediate any one of those 4 ways. It's possible to draw a correct mechanism using any of them. The next one says if something that we don't know what it is undergoes electrophilic aromatic bromination, a possible intermediate is shown below. That must be this. Draw the other 2 resonance forms. Same type of game. We just want to shift around that plus charge. And the rules state that the way we do that is by moving a double bond over. So that's one resonance form. And the other resonance form moves this double bond over and leaves the plus charge on that carbon. So those 3 carbon atoms share the plus charge. and then circle the worst resonance form, well, that's going to be the one with the plus charge right next to the highly electron withdrawing trichloromethyl group. How do you know that's electron withdrawing? Because you've got a carbon atom with 3 electronegative chlorines attached to it. That carbon atom is very electron poor. And putting a plus charge right next to it, or a partial plus charge right next to it, just makes the whole thing worse. And that's not surprising, because here we've started to do bromination para to this electron withdrawing group. We've been very clear in class that electron withdrawing groups are meta-directing, not orthopara-directing. And this is the reason why. If we tried to do substitution at the para or ortho positions, you get a resonance form like this, which is especially disfavored because you're putting a plus charge right next to an electron poor atom. So the system avoids doing that by doing meta substitution. That way you get 3 resonance forms, but at least none of them puts the plus charge right next to an electron poor atom. So that's the reason why electron withdrawing groups are meta-directing. It's because if we tried to do ortho or para substitution with an electron withdrawing group on the benzene ring, we get a very disfavored intermediate. It's not great if we do ortho or para substitution, but at least with meta substitution. It's not great with meta substitution, but at least with meta substitution, we're never putting the plus charge right next to an electron poor atom. So that one is the worst resonance form. And then finally, of these 5 species, circle the species that is aromatic. There is exactly one such species. Well, we can cross these out one by one. We were very clear that cyclooctatetraene is not aromatic because it has 8 pi electrons. That's the wrong number of pi electrons. It turns out further that cyclooctatetraene is not planar. And I gave rules in the chapter 15 notes by which you can know whether something is going to be planar or not. One thing I've noticed is ring sizes larger than 6 are able to be non-planar, and some 6-membered rings too. But I put all that in the chapter 15 class notes. So if you're looking for how to know when something's planar and how to know when something can be planar or can't be planar, take a look at that. With 8 atoms in the ring, we're well able to be non-planar. And the reason cyclooctatetraene does that is to avoid being anti-aromatic. This question is not asking about anti-aromatic versus non-aromatic. That's a question that doesn't interest me very much. My main concern is, can you tell about a molecule? Yes, this is aromatic. No, this is not aromatic. I've said that in class, and I've been very clear about that. In any case, cyclooctatetraene is not aromatic. Whether it's anti-aromatic or not, it happens not to be. It's just non-aromatic. And cyclooctatetraene behaves like any other normal alkene. It undergoes addition reactions when you treat it with electrophiles. It behaves just like ethylene. What else do we know is not aromatic? I don't feel like counting all the carbons in this ring, but I guess we might as well get it over with. Let me see if I can mark one of them so we know we started there. Perfect. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 carbons is going to turn out to be a bad number. That's going to have 2, 4, 6, 8, 10, 12 pi electrons. 12 pi electrons is the wrong number. 12 pi electrons doesn't fall into the series 2, 6, 10, 14. So it's got the wrong number of pi electrons, irrespective of whether it's planar or not. I suspect it's not. But we don't need to know that in order to answer the question. All we need to know is that it's got the wrong number of pi electrons. It breaks Huckel rule number 4. So that one's not aromatic. The cyclopentadienyl cation is a familiar species. There's only 2 pi bonds, so there's only 4 pi electrons. 4 is the wrong number. 4 doesn't fall into the series 2, 6, 10, 14, etc. So the cyclopentadienyl cation fails Huckel rule number 4. In fact, the cyclopentadienyl cation is also anti-aromatic. It's only a 5-membered ring. It must be planar. So it's kind of like cyclobutadiene in that regard. It has no choice but to be planar. The ring is too small to pucker out of planarity. But whether it's anti-aromatic or not, it's certainly not aromatic. Of the two that are left, we can rule out this one because this one, cycloheptatriene, has a CH2 in it. That's an sp3 hybridized atom. So game over. That one's not aromatic. That leaves this one, which if you didn't know from class, that's pyridine. Pyridine is an aromatic species. It's isoelectronic with benzene. So pyridine is the one that's aromatic. The others are not aromatic. In this case, we didn't even have to draw any diagrams. If we were to draw the diagram of pyridine, it's actually kind of hard to draw the diagrams on ChemDraw, but I'll show you how to do it all the same. I'll do the best I can. Let's put our nitrogen over here. It can go anywhere. We don't really have to. We've got our 3 pi bonds. Where are my p orbitals? Do I have p orbitals? Oh, I do. Look at this. There's one here, one here, one here, one here, one on the nitrogen, and one over here. So remember the rules. The rules state that every atom that's involved in a pi bond gets 1 electron. So there's 1 electron in this p orbital. That's not good. I need a much larger dot. How can I get a, oh, I know how to get a really big dot. I write a period and make it like 48. There's a dot for you. One goes in here. One goes in here. One goes in here. One goes in here. One goes on the nitrogen because it's involved in a pi bond. And the last one goes over here. So all 6 of those p orbitals have exactly 1 electron in them. The only thing left is the nitrogen and its lone pair. We need to account for that lone pair, and there is a place for it. Namely, the sp2 hybrid orbital extending outward from the ring. That's going to have, that needs to be filled, first of all. And the only thing that we can't put into sp2 hybrid orbitals is pi electrons. All the pi electrons are accounted for. The only thing left is the lone pair on nitrogen, which needs to go into that sp2 hybrid orbital. That fills the sp2 hybrid orbital, that takes care of that problem, and it also accounts for the lone pair on nitrogen. There is no way you can just look at the structure of pyridine and know where that lone pair is. It's not possible. You have to draw the diagram. Once you do, it becomes clear that this is an aromatic 6 pi system. There's 6 pi electrons, and the lone pair on nitrogen is not part of the pi system. So that's the only one that's aromatic. That's the only one that is the right number of pi electrons. These 3 have the wrong number of pi electrons, and this is an sp3 hybridized atom. So they're ruled out. So pyridine is aromatic. Good. That leaves us about half an hour to get through the rest of the exam. We're still recording, that's good. By sometime tomorrow afternoon, let's say, this should appear on YouTube. All right, so these are questions like we practiced today in class, where you're given the starting material and the reagents and asked to draw the product. I could also give you the starting material and the product and ask you for the reagents. Those are fair game for the exam as well, and I think we have a couple of questions like this. So we know from the reagents that we're going to be replacing a hydrogen with a nitro group, NO2. That's electrophilic aromatic nitration. The question is where to put it. Well, one of the things we learned in class today, since both of these groups are orthoparadirecting, we need to know which one is going to decide where the nitro group goes. And the answer is whichever of the two groups is more activating. And that's going to be the methoxy group. The methoxy group is more electron rich than the chlorine. It's further to the right of that diagram in your book. So the methoxy group is going to decide. So we want the nitro group to go, wherever that methoxy group decides. And the methoxy group is orthoparadirecting, so the nitro group could go here, the nitro group could go here, or the nitro group could go up here. And in class, we said if you're ever in doubt, you want to put the new group where there's the most room for it. Clearly, right there is no good, because that's right between the chlorine and the methoxy. We can rule that out. Of the other two positions, one is next to the chlorine and one is next to the methoxy. We said that you want to put the new group next to the smaller group, and we defined the smaller group as the one with fewer atoms, and the larger group as the one with more atoms. Well, that's easy. Methoxy is 5 atoms, chlorine is just 1 atom. So the correct answer has the nitro group next to the chlorine. Whoops. Like this. That's going to be the major product, I would predict. The next reaction is one you talked about in Organic 1, but we're going to review on Monday. In Organic 1, we learned that NBS, which is N-bromosuccinimide, N-bromosuccinimide, just to remind you, has this structure. You do need to know the structures of these things, not just memorize letters. These should all mean something to you, should call up a structure in your mind. So this is NBS for N-bromosuccinimide. And NBS is an oxidizing agent. It's also a powerful brominating agent. And one thing that NBS does is it replaces all benzylic and allylic hydrogens with bromines. And benzylic and allylic are 2 words that you need to know. If you treated this compound with only one equivalent of NBS, I think you'd get a mixture, because there's 2 locations where we have benzylic hydrogens. One is this CH2, those hydrogens are benzylic, and the other is the CH3, those hydrogens are also benzylic. But with an excess, it's clear. We just replace all benzylic and allylic hydrogens with bromine. So these 2 hydrogens would be replaced with bromine. And the 3 hydrogens on the methyl group would be replaced with bromine. So I think you'd get that compound as the major product. It doesn't touch any of the other hydrogens. It leaves those alone. So if you've forgotten the definition of benzylic and allylic, please look that up. We've given that definition in class and in the class notes. They're two words that you need to know what they mean. Benzylic basically means next to an aromatic ring. Allylic means next to a carbon-carbon double bond. Not in the double bond, but one carbon over. So I think that's the best answer. Over here is another reaction we're going to talk about on Monday. We're going to say that potassium permanganate, it's one of the strongest oxidizing agents known. When you treat an alkyl aromatic compound with potassium permanganate, it chews off all of the alkyl carbons and oxidizes all of them except the one attached to the benzene ring to CO2. So they become inorganic. The carbon atom that's attached to the benzene ring is oxidized all the way up to a carboxylic acid functional group. So again, you need to know what a carboxylic acid is. And we'll go over this reaction on Monday. So I would expect the major product would be this carboxylic acid. The chlorine would be left alone. The other carbons in the propyl group get oxidized to CO2. The organic product is like this. The only exception to this is if the benzylic carbon is quaternary. So if I didn't want to do that. So if, for example, our starting material looked like this, if that were a quaternary carbon, no reaction. You need at least one hydrogen attached to that carbon to be able to oxidize the carbon up to a carboxylic acid. If the benzylic carbon is quaternary, there's no reaction. But in all other cases, it doesn't matter what the alkyl group is. It can be 1 carbon, 2 carbons, 20 carbons. Doesn't matter. All of the other carbons go away and are oxidized to carbon dioxide, and the benzylic carbon gets oxidized to a carboxylic acid. So we'll go over that reaction on Monday as well. In this problem, we're doing an electrophilic aromatic substitution. These are the reagents for Friedel-Crafts alkylation. In other words, we're going to replace a hydrogen with a tert-butyl group. And the only thing we need to do is figure out where that tert-butyl group goes. This ester group is meta-directing. We know that because there's a carbonyl group directly attached to the benzene ring. That's a meta-directing group. So that means the tert-butyl group will go meta to that ester group. And you can draw it on either side. Looking something like this. That I would expect to be the major product. And the last question here is actually from Organic 1. I've said repeatedly that I still expect you to know all of the Organic 1 reactions. This was a reaction we did in Chapter 8. That was one of the alkene addition reactions. MCPBA is a peroxy acid. There are others besides MCPBA. We said when you treat alkenes with a peroxy acid, you get an epoxide. Which means we delete the double bond and we build a 3-membered ring in place of the double bond with an oxygen as the 3rd member of the ring. So that's the general structure of the product. But one thing we notice is that we've got chiral carbons. So that means we need to show stereochemistry. And there's 2 enantiomers. You could draw this enantiomer, or you could draw the opposite. You could also draw these 2 wedge bonds as dot bonds. but either answer is acceptable. You can make these two wedge bonds dot bonds, and that dot bond a wedge bond. That's just the other enantiomer. The directions are clear. You must account for any applicable relative stereochemistry. That means if your product is chiral, you need to show only one enantiomer. You don't draw both enantiomers. You draw just one of them. But either of those is acceptable. So MCPBA converts an alkene to an epoxide. That's a chapter 8 reaction. Good, so much for those questions. Oops, I did that wrong. Over here, we have some problems of the type I mentioned. These are ones where you're given the starting material and the product, and you need to come up with the reagents. Both of these are reactions that we'll go over on Monday. You will have to know them. They are fair game for the exam. In the first one, I think you'll agree we've taken the benzene ring and turned it into a cyclohexane ring. That's a reduction reaction. We need to reduce the benzene to a cyclohexane. That's done with catalytic hydrogenation. But palladium is ineffective on benzene rings. Palladium will work as a catalyst for alkenes. With benzene, you need harsher conditions. So you need not only excess hydrogen, you need rhodium metal, RH. That's the reagents you need to do that. You will notice that the two OH groups wind up cis to one another. That's another aspect of the reaction that you have to know. If there's any stereochemistry involved in the product, you need to show all the groups being cis. And if you don't show that, you will lose points. You need to be aware of the stereochemistry of reactions. So if you just put OHs with straight lines, you would get part credit. But for full credit, you need to show that the two OH groups are cis to one another. Of course, in this case, you're given the product and you just need the reagents. So you need to know the reagents. In the second one, we're converting hexafluorobenzene to this compound. This is actually a nucleophilic aromatic substitution reaction. The way you know that is because we're replacing a halogen with another group. One of the things we've pointed out about electrophilic aromatic substitutions is that you always replace a hydrogen with another group, always, for every electrophilic aromatic substitution. Here we're not replacing a hydrogen, we're replacing a halogen. And that's the sign that you've got a nucleophilic aromatic substitution reaction. So we need a nucleophile made of an isopropyl group with an O on it. So you need O minus over here. And this is probably going to be sold as an alkali metal salt. You don't even really need to write the sodium, I don't think. But probably the counter ion is sodium. That's the most common one. And then for a solvent, the most logical one is the conjugate acid, isopropanol. So those are the two reagents I would use in this nucleophilic aromatic substitution. We'll learn the mechanism of that on Monday. They're all the same mechanism. And we'll go over this reaction then. And I think with that, all we have left is mechanisms. Four mechanisms to be precise. So the first one is just conversion of nitric acid and sulfuric acid to the nitronium ion. This is part of the mechanism of electrophilic aromatic nitration. Notice the directions for mechanism problems. You need to account for formation of the product shown. Actually, it says major organic product shown, and I admit not a one of these things is organic. But that's still a reasonable mechanism question. So we need to account for formation of the product shown from the starting materials shown using the reagents shown. We're not given any other reagents. But we talked about this mechanism in class. We said the first step is protonation of the OH oxygen using sulfuric acid. So instead of OH, you'll have OH2 plus, like that. In the next step, we lose the water molecule by the oxygen on the O minus donating an electron pair in towards nitrogen. And we have to break a bond. We can't leave nitrogen with 5 bonds. So we lose water. Water is a good leaving group. And that goes straight there. So this only asks for that part of the electrophilic aromatic nitration. I could have done the entire thing, including the benzene derivative. This is just asking for this. So you only need to show the mechanism for what you're asked. You don't need to do anything that you're not asked to do. Good. This next one is, again, a nucleophilic aromatic substitution. The way you know is we're replacing a halogen, chlorine, with something else on a benzene ring. That's going to be a nucleophilic aromatic substitution. And I won't spend a lot of time on this because we're going to cover it on Monday. But the nucleophilic aromatic substitution has only 2 steps. In the first step, whatever you're given as the nucleophile attacks the carbon that's bearing the halogen. So the first thing we need to figure out is what our nucleophile is. In this case, our nucleophile is NH2 minus. The way you know that is because we're given NaNH2. And one of the things I'm going to make a huge point of on Monday is that when you're given alkali metal salts, the alkali metal doesn't play any role in the reaction. So NaNH2 is NH2 minus, just like NaOH is OH minus. NaOCH3 is CH3O minus. You don't even write the sodium. It doesn't play any role in the mechanism. It's just a counterion. So in the first step of a nucleophilic aromatic substitution, the nucleophile attacks the carbon that bears the leaving group, and we break the pi bond and put the electrons onto carbon. So that arrow means we're taking the 2 electrons in the pi bond and putting them onto the carbon atom to generate a carbanion. And you get a resonance stabilized species. So we have the chlorine still there. We have the NH2 that we just formed a bond, and we have this carbanion. That carbanion is resonance stabilized. There are at least 2, oh my, why is that so tiny? That's better. I totally lost my train of thought. Oh, the intermediate is resonance stabilized. The minus charge could also go on this carbon or on this carbon. You can use any of those resonance forms in the mechanism. It's fine. But from this resonance form, the way you'd show the rest of the mechanism is pretty straightforward. This electron pair folds back in to regenerate the aromaticity, goes back between those two carbons, and we lose the halide ion leaving group. And that gets you straight to the product. So a nucleophilic aromatic substitution has two steps. What it doesn't have is one step. If you drew this as an SN2 reaction, with this attacking here and the chloride leaving at the same time, that would be wrong. That would lose points. It is not an SN2 reaction. It takes two steps in order to do a nucleophilic aromatic substitution. And that's it for that page. There's just two more mechanisms, and then we're done. Four of you have really stuck through the whole thing here. I hope you're getting ready to see cats, because that will surely happen. So these are both electrophilic aromatic substitution reactions. So they're both pretty much going to have the same mechanism. The first one is a Friedel-Crafts alkylation, where we start with isobutyl bromide, but we get the tert-butyl substituted compound. The reason for that is because we're going to get a carbocation that will undergo a hydride shift and rearrange. Notice that the tert-butyl group goes meta to the nitro group, just as we would have expected. Nitro is a meta-directing group. So the reaction starts not with the benzene ring, but with the alkyl halide. This is how we did it in the class notes. So our goal is going to be to get rid of the halide. Our catalyst is aluminum bromide. It could just as easily have been iron 3 bromide, same mechanism. So it starts with the relatively electron-rich bromine atom donating its electron pair toward aluminum. We did one of these in class today. So the aluminum will now have a minus charge, as it would if it were iron. The bromine has a plus charge. Like that. The bromine really doesn't like to have that plus charge. So the plus charge on bromine makes this carbon-bromine bond especially weak. We break that carbon-bromine bond and put the electrons onto bromine. That gets rid of the plus charge on bromine and leaves behind an isobutyl carbocation. CH2+. That's a primary carbocation. We can rearrange to a tertiary carbocation by doing a 1,2 hydride shift and moving over the hydrogen next door along with its electron pair. So that's a 1,2 hydride shift, and that's how we show that. We start the arrow at the carbon-hydrogen bond and point it at the carbon that bears the plus charge, and now we have a much more stable tert-butyl carbocation. Now that CH2 is a CH3, and the plus charge is on the tertiary carbon. So in the next step, the electrons from the benzene ring attack that carbocation and form a new carbon-carbon bond. This arrow means that the electrons in the pi bond remain attached to this carbon, and break away from the carbon to the right. We also don't want to forget our nitro group. We want, by all means, that nitro group to be meta to where all this is happening, because the nitro group is meta directing. So that carbon will bear a hydrogen in a nitro group. This carbon, as I said, will have the plus charge on it. Oh, not nitro, I'm sorry. This carbon will have a tert-butyl group in a hydrogen. There's our tert-butyl group. Here's our hydrogen. And so we need now something to pull off that proton and regenerate the aromaticity. We talked about this today. We need something that will accept the proton so the electrons in the carbon-hydrogen bond can go back into the six-membered ring and make it aromatic again. The only thing we have is this tetrabromoaluminate salt, or anion, maybe I should say, that we generated back here. That's where that comes from. This over here is what we get from the step where we form the carbocation. And again, I think it's much more logical to show the electrons in the bond, picking up the proton and making HBr. And once we do that, we've got our product. However you choose to draw that, your tert-butyl group and your nitro group will be meta to each other. So that's a standard electrophilic, Friedel-Crafts alkylation. That's one of the electrophilic aromatic substitution reactions that we learned. And I do want to repeat, the answer key is available on Canvas. But I'm looking at the answer key right now, and it's the same as this. Our final problem looks like an electrophilic aromatic bromination. We have a pre-existing ethyl group on the aromatic ring. Unsurprisingly, the bromine winds up para to the ethyl group, because alkyl groups are orthopara directing. They're electron rich. That makes them orthopara directing. So the first thing we need to show is formation of the electrophile. And you'll recall that the elemental halogen, which will be either Br2 or Cl2, a student today asked me a lot of questions about putting a fluorine or an iodine on a benzene ring. And I had never really looked into it. They're mentioned in the textbook. But looking at the reagents, I actually looked at the structure of select fluor, which is used to replace a hydrogen with a fluorine. And I looked at what's going on in the reaction of iodine with either H2O2 or copper 2 chloride. And I convinced myself the mechanism is basically the same for those two as well. It's still just an ordinary electrophilic aromatic substitution that replaces a hydrogen with a halogen. It just uses a different reagent, that's all. So in case you're curious, for the cases of iodine and fluorine, the mechanism's the same. It just uses more exotic reagents than these. The mechanism starts the same way as with the Friedel-Crafts reaction, by the halogen donating an electron pair towards the Lewis acid catalyst. So we have a divalent halogen. We have our aluminum or iron atom with a minus charge. and the halogen atom with the plus charge, like that. And that makes it real easy to pick off that terminal bromine, because in so doing, we'll be able to break that halogen-halogen bond like that and put the electrons onto the halogen with the plus charge and get rid of the plus charge. This arrow here means that we're using the electrons in the pi bond. The electrons remain attached to this carbon and break away from this carbon. So the carbon on the bottom is going to have the plus charge. That means we want to be sure that our ethyl group goes para to where the bromine's going to wind up. Because in the major product, we would expect para substitution. I'm showing here something I figured out during my second class today, just on the fly. So if you're in the first class, you'll notice what I did here is I drew the aromatic ring and I drew my mechanism first, and then I put on the substituent. That way you can be sure that the substituent goes into the right place. That's a new thing that I just figured out today. Only took me 25 years. So we have that hydrogen still there. That hydrogen was there to begin with. And again, I don't want you guys thinking that hydrogen is something mysterious. It was always there. It's right there. It's just that hydrogen. It was there the entire time. We're only drawing it because we need it in the mechanism. We're showing deprotonation of that intermediate to get rid of the plus charge on the six-membered ring. And so, once again, really the only way we can do that is with a bromide ion. And that halide ion is going to come from the tetrahaloaluminate or tetrahaloferrate salt. I'm going to move that. I think it will look better if I draw it down there. So we take the halogen with its electron pair in the bond, and we break the carbon-hydrogen bond and move the electrons in the carbon-hydrogen bond in between those two carbon atoms and get rid of the plus charge. And that gives you the para-bromoethylbenzene. And that's basically it. That's that mechanism. While the four of you are still here, you deserve some cats. I've kept them out of the room because, as I might have mentioned in class today, I would have left them in the, Barnaby would have been fine to leave in this room. Oh, you can't see me. Barnaby would have been fine to leave in the room. He would just have slept on the floor, slept on the bed or something like that. He's getting kind of old. But Molly's a problem. I have my computer box, you know, the actual computer, the box that holds all the computer parts on the floor. And she likes to jump on that to jump up on the desk to be with me, which is very sweet of her. But when she does that, sometimes she hits the power button and turns the computer off. And we can't have that during our video. All right, where are you guys? Well, Barnaby was resting comfortably, but you get to see him first. So this is Barnaby. He's my adult cat. He is a mutt. He is clearly part Siamese from his coloration, but he's not full-blooded Siamese. His head and body shape are the wrong color. I don't know how old he is. He was a rescue cat, so when I adopted him in 2020, they told me he was between 8 and 10 years old. I think 8 is probably closer to the truth. So I figure he's got to be about 12 years old now. So that's Barnaby. We'll put him down. Where'd Molly go? Little rascal, there you are. Everyone wants to see you. They want to admire you. This is Molly. She's really getting big. She was so tiny when I got her in June. So I'm going to try bringing her in at the end of the semester. And I hope she's nice to you. I had always wanted a calico. So when I saw a calico kitten, I couldn't resist. Where do you think you're going? Everyone wants to admire you. You going? Well, anyway, those are my two cats, or rather my cat and my kitten. So we'll try bringing in Molly on the day before final exams start. It'll be a Wednesday. Barnaby would die if I brought him in. He only likes me. So far, Molly looks like she unfortunately might be turning out only to like me too. Sorry, I have to keep her out of the bathroom. So those are my two cats. Didn't take them long to learn to get along with each other. Good, that's about it. So let me stop the recording. I will see you all on Monday to finish up chapter 16 and look for this video sometime tomorrow. Let's say mid to late afternoon, it should show up. So thank you all. See you all on Monday.